Now, if the kinetic energy of mass m at distance on a circle of radius r, moving with angular velocity omega, is this, then what's the kinetic energy of masses m1 at distance r1 and masses m2 at distance r2, let's say sitting on the same beam or in some way on the same object that's rotating about some axis, so that these two masses are always rotating at these distances, respective distances, from the axis of rotation. Okay? And assume a rigid body, so they're all rotating with the same angular velocity. The whole object goes through the angular positions at the same rate. Okay, so anyhow, what's the kinetic energy? Well, the answer is pretty obvious, and the class got this very quickly. It said, well, you just take this expression for the first mass and the first distance, and then you do the same expression for the second mass and the second distance, and you get it. Because if you have two separate masses, each one has its kinetic energy. And, you know, this would be the kinetic energy of the first object, 1/2 m1 v1 squared, where v1 is the speed of that object. And the second is 1/2 m2 v2 squared, has this kinetic energy, where v2 is its velocity. Okay, well, of course, we don't do this in terms of v1 and v2. We do it in terms of omega and r1 and r2. Now, you have the same omega, so your v1 is r1 omega, and of course, v1 squared is r1 squared omega squared. That's completely obvious. And for your other one, you got 1/2 m2 r2 squared omega squared. And I ask, okay, what can we do with this mathematically? Everybody's good, you know. Okay, factor out the 1/2 and factor out the omega. Okay, well, I'm going to do that. I'm going to factor out the 1/2 on the front and the omega on the back. And it's very clear that this is what I end up with. Nobody needs explanation of that. Everybody understood that instantly. So there we have the expression for the kinetic energy. Now, the payoff here is, I'm going to write this as 1/2 I omega squared, where I is something we're going to call the moment of inertia, and it's just this quantity here. It's the m1 r1 squared plus m2 r2 squared. So that works just fine, and we could have written this expression is 1/2 I omega squared, where I is just mr squared. Because there's just one mass, so it's just 1 mr squared. Whereas here there are two masses, so we got to put subscripts on them, m1 and m2 at r1 and r2, and we get these expressions. And that's going to be our I. Our I is what we plug in here, so we have 1/2 something times omega squared, which has a form identical to that of 1/2 mv squared, except again, we're using I and we're using omega. Okay. If there are n masses, what do you do? Well, you just, you know, if there are 3 masses, then you'd have 3 of these. You'd have an m3 r3 squared, you have an m3 r3 squared added here. They just add up. So you just add them up for all the masses, however many you have, m1 r1 squared plus m2 r2 squared, all the way up to m sub n r sub n squared. And if you got a whole beam rotating about the axis, well, let's see, that beam has a mass of about 170 grams, and it's steel, and you know, steel is about in the order of 60 grams per mole, so you've got roughly 3 moles of steel there, which is around 2 times 10 to the 24th atoms. The atoms aren't really mathematical particles, but they're awfully close, they're awfully small. So all we got to do is add this up to m sub 2 times 10 to the 24th, r sub 2 times 10 to the 24th squared, adding it up for every atom in that beam, and we would get the moment of inertia, and the kinetic energy at angular velocity omega would be 1/2 I omega squared. Now, we don't actually do that for 10 to the 24th atoms, and we certainly, so we assume that the mass is continuously distributed, and we do an integral. And we're not going to do that right now. But this just leads to an integral, and many of the integrals are very simple. And the complicated ones are just too darn complicated, so we just look them up as formulas. Okay, so anyhow, this I is again called the moment of inertia. And we have now this, which is always the case for any object. Any object rotating about an axis has a moment of inertia. And if you try to rotate that object, okay, put a couple of handles on it, try to rotate it, the greater the moment of inertia, the less angular acceleration you're going to be able to give it. So to move it from here to here with the same force, if you have a greater moment of inertia, it's going to take longer than if you have a lesser moment of inertia. Also, the moment of inertia depends on the positions of the objects and the mass, okay? And it goes as the square of the distance of a mass from the axis and the first power of the mass. So if you have the same mass, but change the distances from the axis of rotation, that's going to change your moment of inertia. Now, you know, if you got a bar or a beam and you put masses on the end of it, it gets a lot harder to rotate. If you put the masses close to the center, it doesn't get that much harder. We can also say that if you were to take any set of masses, consider the magnets on the beam that we've looked at, take any set of masses, and the magnets on the beam are distributed from the center on out. Not evenly, but they're distributed in some way from the center on out. If I was to move all those masses out to the ends of the beam, my mass wouldn't change. I'd have the same total mass, but it would be harder to accelerate that system. It'd be harder to get that system rotating at a given rate. So I'm saying now that if you double all the distances from the axis, not only it doesn't just get twice as hard to rotate, it gets 4 times as hard because you have 4 times the moment of inertia. And you're going to have to put in 4 times the kinetic energy to get it up to that velocity, angular velocity, which means you're going to have to do 4 times as much work. You're going to burn 4 times as many Cheerios. Okay? Very simple idea, but it's extremely important. Everything I'm saying here is very, very important and very central to understanding rotational dynamics and rotational kinematics, especially rotational dynamics, okay, which is where you involve forces and torques, as we'll talk about in a minute. So, again, you should understand that doubling all the distances, if you got the same masses, but double all their distances from the axis of rotation, you're going to get 4 times the moment of inertia. Now, I've jokingly used the word forples because somebody came up with that in a class about 100 years ago. I asked a question like this, and I said, now, you double this quantity, what happens to that? And the guy was very good at answering, very bright guy. It forples. Okay, well, it quadruples, but I love the word forples. Sounds, vaguely obscene or something. But that's not why I love it, so it's just a really good word, and it's a really good guy that said it, so I use it. Okay, double the distances from the axis, that forples the moment of inertia. Double all the masses, that doubles the moment of inertia. Because the mass is just there as the first power. The r, the distance from the axis, is squared. Okay. Now I might as well go ahead and wrap this up rather than trying to get another video. If you've got a beam and a force applied at a right angle, now I wasn't very specific about what that right angle meant, but it means that the point of application is here, and a vector from the axis of rotation to that point of application is perpendicular to the force vector. Now there's a more general way to say that about the line of force and the closest proximity to the axis, and we'll talk about that. But right now, just consider a force on a beam exerted in a direction perpendicular to the beam, much like we did with a rubber band chain. Pull the thing back, let the beam go. The rubber band chain stays close to a right angle and gives the beam some kind of kinetic energy. Okay? So you have R here and you have F. Now if you exert F out here, it has much more effect. It results in a greater angular acceleration than if the F is applied here. Okay, you have more leverage on the system out here. That's an intuitive idea, but we'll make it rigorous. Okay, but without getting too rigorous, I'm just going to say, okay, the torque is represented by tau. Okay, the Greek letter tau looks like this, and you can look at even better taus. I think that's actually a fairly good one. And tau is equal to just the product of R and F. Okay? And tau is the quantity that causes the angular acceleration. Okay, or we think of tau as the quantity that results in the angular acceleration. A bigger tau gives you a bigger angular acceleration. So if you got a bigger R with the same force, you got more leverage, you're going to get more acceleration. If you got a bigger force with the same R, well, again, you're going to have a greater torque, you're going to be able to turn that thing and accelerate it more rapidly. Okay? So that's the idea of torque. Now, again, we'll make that formal and in more detail, but probably not for a while. And it's easy to show then that if this is the definition of tau, that by Newton's second law, angular acceleration is equal to tau divided by moment of inertia. Now think about what angular acceleration is. An acceleration just like A, but it's an alpha because it's angular. Tau is like your twisting force. Sometimes it's called a twisting force. Okay, it's the thing that causes the angular acceleration. Okay, and I is the thing that resists the angular acceleration. Just like a force acting on a mass, the force is what causes the acceleration. The mass, and I should call that net force. And while I'm at it, I should have said that this is the net torque, or what it actually stated correctly. Okay, again, you exert a net force on a mass, it results in an acceleration. More net force, more acceleration, more mass, less acceleration, and these are just proportionalities with the first power, okay? A direct proportionality and an inverse proportionality to the first powers of F net and M respectively. Similar here, okay? Tau net causes the angular acceleration, moment of inertia resists it, okay? Net force causes the acceleration of the mass. The more mass you have, less acceleration, so the mass is what resists it. So there's a parallel, and there are many parallels between angular quantities and linear quantities that we'll talk about a little more. But this is kind of the basis of angular dynamics in a nutshell. Again, haven't had complete rigor here. What if the force is at some angle other than perpendicular to this thing? And we formalize that a little bit later. But again, here's how you deal with angular dynamics, okay? Angular motion as a result of forces exerted in given directions at given positions. Forces that are exerted in such a way as to cause angular accelerations. Okay, well, enough of that. You should understand. Okay, this is not difficult to understand once you understand the thing that we spent a lot of time on earlier. Okay, just for the single mass moving at velocity v in a circle of radius r. It all extends very easily. We won't worry about the integral now, but that's actually very simple to write down. And you have torques, and we've experienced those with the rubber band chain and the beam.